Hi everyone. In this section we're going to talk about exponential functions and logarithmic functions. In section 5.1 we begin by covering exponential functions and their graph. We define the exponential function f with base b to be defined as f of x equals b to the x. Okay. These are different than polynomials. If you want to compare some simple ones, let's say x squared, which is our quadratic polynomial, versus a exponential function, which is 2 to the x. The difference being that whenever you have polynomial terms, each individual term has the same exponent, but the base is allowed to vary. Whenever we have an exponential function, now it's the base that's a constant, and the exponent is going to vary. Okay? We require that the base be positive, so we avoid complex numbers, and we want to have a base other than 1, because if we had 1 to the x power, we know that 1 to any power is 1, and that type of function doesn't really fit in with exponential functions. It's more belonging to our class of constant functions that we saw previously. Some common examples of exponential functions include f of x equals 2 to the x. This would be an exponential function with base 2. We have g of x, which is 10 to the x, h of x, which is equal to 3 to the x plus 1, or j of x, which is 1/2 to the x minus 1 power. One of the first basic skills we want to develop is the ability to evaluate these functions. Let's suppose that we have a function f of x, which is 42.2 times 1.56 raised to the x power, and let's suppose that this function models the average amount spent at a shopping mall after being there for X hours. What is the amount spent to the nearest dollar after 4 hours? Okay. So after 4 hours, that's going to be an X value of 4. So we want to go ahead and plug this into our calculator. F of 4 is equal to 42.2 times 1.56 raised to the 4th power. If you have a scientific calculator, like a TI 83 or 84, it would look like this. I'm going to turn it on. I'm going to do 42.2 times 1.56. And now I need the exponent of 4. If you see like a little arrow key like this, that's the exponent. And then we're going to raise it to the 4th power. And then we will hit enter. And to the nearest dollar, it would round to $250. So to the nearest penny, it's $249.93. But again, it's always important to follow the directions. They say to the nearest dollar, so it'd be $250. Okay. If you don't have a scientific calculator like this, if you just have a more basic one, the way that you would want to enter this would be following order of operations. We would have to do the exponent first. So we would do 1.56, raise it to the power, so exponents first, and then after doing so, then you would multiply. So now times 42.2, and that's how you would get the 250. One of the things we're going to now discuss is going to be the domain of these types of exponential functions. We are familiar with expressions of the form b to the x, where x is a rational number. Like, for example, we know how to take and raise things to positive integer powers. We know that negative exponents mean reciprocals. And in other classes, we've studied what it means to have a fractional exponent. A fractional exponent or a rational number exponent is a combination of a power along with a root. So for example, if we wanted to take and raise, let's say, some base b to the 1.7 power, 1.7 is a decimal. It's equivalent to the rational number 17/10. And in terms of radicals and power, this is equivalent to the 10th root of b to the 17th. Similarly, if we wanted to take b to the 1.73 power, that's the same thing as b to the 173/100, which would correspond to the 100th root of b to the 173. But let's suppose we wanted to raise some base to an irrational number. Like for example, like b to the square root of 3 value, or b to the pi, which would be to like the 3.1415 ... that power that never stops. How exactly can we make sense of something like this? Let's kind of pick on the square root of 3 for a moment. We know that this is an irrational number, and that means that it is not possible to write it as a ratio of two natural numbers. Okay. The square root of 3 itself is approximately 1.73205 ... What we can think of is if we kind of approximate the square root of 3 by chopping off a certain amount of its digits, by leaving off some digits, what we have is a situation where we actually have a rational number. So if I look at just the first two digits of radical 3, we would get b to the 1.7 power, which again we can convert to a series of roots and powers. What if instead we include more digits? What if we now look at b to the 1.73 power? Again, that's one we can do with traditional methods. That's also a combination of a power and a root. And the idea is that if we continue to take these exponents to get closer and closer and closer to radical 3, these corresponding intermediary values, which we can evaluate using roots and powers, those sequence of numbers will approach a theoretical limit, and that limit we would define as b raised to the square root of 3 power. Okay. For us, the biggest takeaway from this ultimately is going to be that exponential functions have domain all real numbers. So whether you want to take a base and raise it to a rational number or an irrational number, the domain of these functions is going to be all real numbers. These functions are also going to end up being continuous, meaning their graph will have no holes, no jumps, or no breaks in it. Okay, so whenever we graph a exponential function, we should be able to do so in a nice manner where we can graph the entire function without having to lift our pencil off the paper. To begin, let's graph f of x equals 2 to the x by making a table of values. And I want to use a few negative values. I want to use 0, and let's use a couple positive values. For the first one, if we plug negative 2 into the function, that'll give us 2 to the negative 2 power, which would be 1 over 4, meaning the point negative 2, comma 1/4 will be on there. 2 to the negative first would be 1/2, that's 1 over 2. So we get the order pair negative 1, comma a half. If we plug in 0 into the function, anything to the 0 power is 1. If we do 2 to the first, we get 2. So we get 1, comma 2. And if we raise 2 to the second power, we get 2 squared, which is 4. Let's begin by plotting these points and see if we can kind of notice a pattern here. So we have the order pair, and let's zoom in a little bit. We have the order pair negative 2, comma a fourth, which would be roughly about here. At negative 1, we had the order pair negative 2, 1. We had 0, 1. We had 1, comma 2. And then we had 2, comma 4. And essentially what's going to happen, if we look at the positive values, very quickly we can see that these are going to double for each value of x you go to the right. So we went from 1 to 2 to 4. If we're adding another power of 2, for example, 2 cubed would be 8, which would put us up here. And we see that as we go to the right, this function is going to rise pretty rapidly. Every time you go over 1, you're going to a height that's exactly twice your previous height. So this thing grows very, very, very fast. On the other hand, what's going to happen as x approaches negative infinity? Well, if we keep taking larger and larger powers, negative powers of 2, what's going to end up happening is we're going to get values that are smaller and smaller and smaller and are ultimately going to approach 0. Okay? So it turns out that these functions will have horizontal asymptotes, and for this particular function, it's going to have a horizontal asymptote of y equals to 0. And the reason for that, as we just mentioned, as x approaches negative infinity, the values of the function will approach 0. This is a very important type of graph. We want to memorize this one. This is the graph of 2 to the x. Let's do the same thing. Let's see if we can graph 1/2 to the x by again making a table of values. So I'm going to use the same inputs. Let's try -2, -1, just so we get a couple negative numbers. If it's in the domain, you always want to use 0, and here that's the case. And let's use a couple positive values. Let's use 1 and 2. If we plug -2 into the function, we get 1/2 to the -2nd. That's going to be equal to 4. 1/2 to the -1st power, that's going to be equal to 2. 1/2 to the 0 power is 1, because anything to the 0 power is 1. 1/2 to the 1st is 1/2. And if we take 1/2 squared, that's 1/2 times 1/2. That should give us 1/4. So we get the following ordered pairs for this graph: -2, 4, -1, 2, 0, 1, 1, 1/2, and 2, 1/4. Let's go ahead and plot these ordered pairs on the graph. We have -2, 4, -1, 2. We have 0, 1. We have 1, 1/2, and then we have 2, 1/4. Okay, so you kind of notice the pattern and see what's happening here. This time, as we go towards negative infinity, the function is going to rise rapidly and approach positive infinity. And as x approaches positive infinity, these function values are going to approach 0. So once again, we do see that this graph also is going to have a horizontal asymptote at y equals to 0. In many ways, it's going to be the case that the graph of 2 to the x, which has y-intercept of 0, 1, and opens up in this way, and the graph of 1/2 to the x, which also passes through 0, 1, but kind of goes in the other direction. These two are kind of the classical examples of the two types of exponential graphs that you can see. So to kind of summarize, these are the characteristics of an exponential functions graph. The domain of an exponential functions graph is going to be all real numbers. After all, whether you looked at the two examples we just did, whether the first one or the second one, the graph goes all the way to the left and the graph goes all the way to the right. Therefore, the domain is all real numbers. The range is going to be the set from 0 to infinity. Again, 0 is a horizontal asymptote. So these graphs will never, ever make it all the way down to 0. So 0 is not included, but it will get as close as you like. And either one of them on one end will approach positive infinity. So we get a range that is 0 to infinity. The domain of these graphs is from negative infinity to positive infinity. One of the most important points that's going to be on these graphs is the y-intercept. It's going to be the order pair 0, 1. The second thing that we want to kind of talk about is how do we know which of kind of the two types we get, okay? And when I mean two types, the exponential functions will either look like the graph in 1, and this occurs when the base is bigger than 1. So, for instance, if you think of the graph of like 2 to the x, because that base is 2, which is bigger than 1, that's why the overall curve and shape opens up like this. On the other hand, if we happen to have a base that's between 0 and 1, think about something like 1/2 to the x. Because that 1/2 is between 0 and 1, that's what's going to give the exponential function a shape that overall looks like this. So if you want to, a lot of times I'll refer to them as like type 1 and type 2, and it's entirely characterized based upon the type of base that we have. Bases that are bigger than 1 look like this. Bases that are between 0 and 1 look like the curve in red. The way that the base shape will kind of impact it is, for example, if we try to compare side by side, let's say 2 to the x versus 3 to the x. They're going to have more or less the same overall shape, but the difference will be just minor details in terms of how each one rises or falls. For example, the graph of 2 to the x, and I'll do that in kind of aqua here, it's going to look like this. Whereas the graph of 3 to the x is going to have the same shape, but what's going to happen is it's going to rise a little more quickly over here, and it's going to fall a little slower like this. So the shapes of these two are going to be awfully similar, but what will change is kind of the way that they rise or fall. And then the last kind of comment we want to make, they are one-to-one functions. If you recall, they did pass that horizontal line test. We will come back to this in the next couple sections. But the other thing that we want to kind of keep track of is the fact that these do not touch the x-axis. There is no x-intercepts, but we do have a horizontal asymptote, which is y equals to 0. If we know the basic shape of these graphs, then we can graph some related ones by using our transformation section we learned previously in the class. So for example, we know that if we have a parent function, we know what the transformation looks like, so whether we add, subtract on the inside or outside of the function, as well as whether we multiply on the outside or inside of the function in terms of stretches and translations and shifts. For example, if they want us to use the graph of 3 to the x to obtain the graph of g of x equals 3 to the x plus 1, first thing we want to do is kind of relate the two. The plus 1 is happening on the inside of the function, which for an exponential function is the exponent. And we recall that if you add 1 inside the function, that's going to be a horizontal shift. In particular, it's going to be a horizontal shift to the left. So it horizontally shifts one unit to the left. So let's begin this one by graphing our parent function. Let's graph 3 to the x. So I'm going to begin by graphing 3 to the x. Couple key features. We know that we have a y-intercept of 0, 1. If I plugged 1 into the function, 3 to the first power is 3. 3 to the second power would be 9, for instance. Over here, 3 to the negative 1 would be like a third. 3 to the negative second would be like 1 over 9. So it does fall really rapidly. And so the graph would look like this. This is the graph of 3 to the x. What we are now going to do is we're going to take each point and we're going to shift it over 1 unit to the left. The important points to keep track of are the intercepts. So this original intercept was at 0, 1. It's now going to get moved 1 step to the left, and that's going to occur at negative 1, 1. If you have a few points, it kind of makes it a little bit easier. You can just take each of those points, move it 1 step to the left. The horizontal asymptote will still stay in the same direction. if you take a horizontal line, the original horizontal asymptote for 3 to the x was y equals to 0. If you take a horizontal line and you shift it horizontally, it still stays in the same spot. So this would be our final answer. The graph that's in orange here would be the graph of 3x plus 1. It was found by knowing the parent graph's shape of 3 to the x, recognizing that we're adding 1 inside of the function, and we recall from our transformation the effect that that has is it shifts the graph to the left 1 unit. Let's take a look at another one. Here we want to use the parent graph of 2 to the x to graph g of x, which is 2x minus 3. We see that we're subtracting 3 on the outside of the function, so that's going to be a vertical shift. And it's going to go down 3 units. So let's begin with the parent graph. Let's graph 2 to the x. We just did that a moment ago, so we know what that graph already looks like. Should look like this. It had an original horizontal asymptote at y equals to 0. And now what we're going to do is we're going to take each point that was on that graph and we're going to shift it down 3 units. So the point that was originally at 0, 1 is now going to get moved to 0, negative 2. The point that was at 1, 2 is now going to get moved to 1, negative 1. The point that was at 2, 4 is going to get moved down to 2, 1. This point over here, which was at negative 1, a half, is now going to occur at negative 1, negative 3 and a half. Should be negative 2 and a half. And our asymptote's also going to get moved this time. If the original asymptote, horizontally that is, if the original horizontal asymptote was at y equals to 0, that asymptote is going to get moved down 3 units, and so now it's going to occur at y equals to negative 3. Once we have a few points, we know the general shape of this thing, and we know where its asymptote is going to be at, we can go ahead and do the graph. So this would be the graph of 2 to the x minus 3. One of the most important bases that we're going to have that occurs a lot in the natural sciences is the natural base e. The natural base e is actually a number. It represents the number 2.718281, etc. And the exponential function, whose base is equal to the natural number e, is called the natural exponential function. One of the things to keep in mind is that whenever you're working with e, at the end of the day, it is an irrational number, much in the same way that pi or the square root of 2 is. And if we wanted to graph this function, one of the things we would know in terms of its shape is that because e is a number that's bigger than 1, it should have kind of like that type 1 exponential graph shape to it. It's going to have a y-intercept of 0, 1, because if you plug 0 into the function, we would get e to the 0, and anything to the 0 power is 1. So we would get that. If you plugged 1 in, notice that we would have f of 1, which would be e to the first, which is e. So when x is 1, we're at that value, which is e, which is about 2.718, etc. And because we know what base value is that's bigger than 1, it should look like a type 1 exponential graph. So the graph of e to the x is very similar to that of, let's say, either 2 to the x or even 3 to the x.